Great. Yeah, hi everyone. Thanks very much for having me today. I'm Beth Lomax. I'm a research fellow at ESA ESTech, and today I'm going to talk about some preliminary results from a research project we're working on. We were sintering lunar regolith pellets for FFC molten salt processing. So firstly, some research context. Molten salt electrolysis, or the FFC process, is a process we're working on to extract oxygen and metals from lunar regolith. So we primarily in the lab used lunar regolith simulants, as with most ISRU activities. And that's a picture showing there the before and after of the material after we've extracted most of the oxygen from it, leaving a metal product. But of course, it's of great interest as to how this process would react to real lunar regolith. And so we applied for 4 Apollo samples, and we're lucky enough to be allocated 1 gram of each. And so we've got 2 immature, 2 mature, 2 Mare, and 2 Highland samples. And so the primary research question there is, how does the reduction of real lunar regolith using the FFC molten salt process compare to the simulant behavior? Because the samples are quite small and we wanted to, large for Apollo samples, but small compared to what we normally process, and we wanted to do a repeat with each sample, we're processing 500 milligrams at a time. So we've built a miniaturized small electrolysis cell, and then we have to figure out a way to retain the material in the salt. So that means that we've decided to sinter it into a pellet prior to processing, so we don't lose it as a powder in the salt. So this means that we can look at a secondary research question, which is what impact do the material properties have on the sintering behavior of the real lunar regolith? And so that's what I'm going to talk about today. And as I said, these are preliminary results. I was hoping to have completed the data set by the time I was presenting today, but we've just done 1 of each sample so far. So we're still waiting for the second half. So briefly, what is sintering? So we're forming a solid mass from a powdered material. We're gluing the particles together without them being fully molten. So just a kind of edge-to-edge contact. And why is it useful to understand and predict the sintering behavior? So we might use sintering for pre-processing, for simplified sample handling, and like in this case. Sintering is also used widely in manufacturing and construction. And we might just want to avoid sintering altogether, like avoid clogging something like a fluidized bed reactor or some kind of transport system. And in general, we might have limited information available, so we might not know the melting behavior of the material that we're working with, but we might have information like the composition. And then the other concept to quickly touch on is what is soil maturity? So it's a degree of surface exposure, and so it's more space weathering. And in this case, the most relevant concept is the more bombardment from micrometeoroids. So the mature material has a lower average particle size, more glassy agglutinates, and more nanophase iron proportionally. So very quickly, the sintering procedure was defined by priorities. So the first being, don't lose the sample. And so we wanted to avoid irreversibly melting it to the crucible. And so we did a very slow, stepwise sintering process using a traditional furnace sintering, slowly increasing the temperature each time and holding it 1 hour at each temperature and then analyzing the material. And the second priority was, again, don't lose the sample. But in this case, we wanted to avoid losing it in the salt during the processing. So we didn't want the pellets to be friable and have particles coming off them. So we monitor the process using XCT until it's very well sintered. And finally, we do want to aim for the best possible properties for FFC processing. So that means we need to maximize the open porosity because we need salt flow through the materials. So it's worth saying that even though these are little bricks, they're terrible construction materials. They're extremely porous, and they're not bricks in that sense. They're trying to be as porous as possible. And so we didn't apply any pressure. We just had a loose powder bed and sintered that. And also we avoid over sintering and closing off the porosity by creating a glassy surface. So it's a picture of the Apollo 15 material. You can see how cohesive it is, being turned on its side, and just a comparison of the colors of some of the Mare and Highland material there as well. That shows all 4 small pellets after sintering. They look quite similar, even with the variation in location. And that just shows where 1 of the samples, the Apollo 16 material, was collected. And so on to the results about the sintering behavior. So we first started by kind of predicting the behavior relative to one another using their composition, so using the oxide composition. And from this, we might expect that the sintering temperature of Highlands material would be about 80 to 100 degrees higher than Mare. We'd also maybe expect that the Apollo 11 material would sinter at a slightly higher temperature than Apollo 15, and that Apollo 16, because they have quite similar compositions, would sinter roughly at the same point. And so this chart shows the observed temperatures that we saw. So the red being the final sintering point when the material was very well sintered, and the blue being the sintering onset, so when it first shrunk away from the walls of the crucible and was removable as a pellet. And so here we can see that the Highlands material in general does sinter at a higher temperature than the Mare material. That can be reasonably well predicted with the composition. However, the other two predictions, we don't see that at all. So we would expect the Apollo 11 to have a higher sintering temperature than Apollo 15, but in fact it's quite a bit lower. And we see quite a variation in the Apollo 16 materials as well. So to examine this, we can compare the observed temperature to the oxide average temperature to look at the ratio. And here we see a really clear separation between the immature material and the mature material. We also see quite a difference in the, I call it the speed of sintering. So the point of sintering onset, and then the point between there and the point where it's well sintered. So some preliminary conclusions based on the first data set, that Mare regolith sinters at a lower temperature than Highlands regolith. Mature regolith will have a lower sintering temperature relative to immature regolith of a similar composition. Mare regolith will sinter faster than Highlands regolith, and mature regolith will sinter lower relative to immature regolith of a similar composition. So looking at those conclusions that relate to the maturity of the sample, we can compare it to what maturity really means. So here we can compare the ratio observed to the average particle size and the agglutinate content. And we see that both of these correlate really well with the final sintering temperature that was observed. It's not surprising that they both correlate because they also correlate to each other. So trying to tease out the difference between particle size and agglutinates is one of the next steps in the project. So this maybe suggests that the final sintering temperature of a given material might be able to be predicted based on a combination of the composition and the particle size or agglutinate. However, we see quite a poor correlation with the sintering onset, so the first shrinkage of the material. And then when we compare the ratio to the proportion of nanophase iron, there we see a better correlation with the sintering onset temperature. This possibly suggests that the glassy rims on these particles, on these mature particles, are gluing particles together prematurely, but not actually changing the overall phase change behavior of the material. That might be why they stick together earlier in the process. And so this is just quickly to show that we're monitoring the porosity throughout the sintering process. So we can see the porosity as it changes with temperature, and looking at other methods of monitoring the sintering, degree of sintering as well. Like, for example, looking at the proportion of the particles that are joined together using image analysis. And just quickly to show you some of the difference in the structure. So we see quite big, large differences between the materials. The mature material has a much more closed, dense structure, more shrinkage, lower porosity, and more closed pores, which is unsurprising given the difference in the particle size, average particle size. And the porosity and shrinkage both correlated to particle size, and the structure for this project will likely impact the molten salt processing quite significantly. So I just wanted to show this video because I think it's quite cool. It's not really related to the project, but it's during the XTT analysis, we saw this spherical glass hollow bead in one of the Apollo 16 samples. I think that's quite interesting. So the preliminary results show that the soil maturity impacts sintering behavior, and that the behavior can be linked to both chemical composition and the physical properties relating to soil maturity. And so we might be able to predict the behavior using a combination of these things. We see a large variation in the sintered pellet structure. And so ongoing work is obviously we want to sinter the second set of Apollo samples. Now that we know where the temperature is expected to be, we can define a more structured sintering process, the set number of steps, for example. And we want to examine the difference between particle size and glass content using simulants with different additives of different percentages of these things. And also then finally, of course, complete the second half of the study, which is the process these pellets using molten salt electrolysis. Yeah, thank you very much.